Last time we began our analysis of the Thompson sampling algorithm by establishing a relationship between binomial distributions and beta distributions with independent parameters, with integer valued parameters, sorry. This time we are going to continue our analysis of Thompson sampling. So let me share screen with you. Okay. So we want to obtain bounds on the regret of the Thompson sampling algorithm. We are going to continue looking at the setting of two Bernoulli arms. The generalization to any number of Bernoulli arms is not hard, but in order to minimize notation and keep things simple, we'll just look at the case of two arms. So let's denote by n sub I the number n sub I of t, the number of times that I has been played in the first t rounds. And we'll denote by s sub I of t the number of successes observed in these NIT plays of arm I. So the parameter mu I, the success probability on arm I, is unknown, and we express our lack of knowledge of this parameter by putting a prior distribution on it. Okay, so we represent our lack of knowledge as a probability. And the prior we choose is a beta prior with parameters 1 and 1, which is in fact the uniform distribution between 0 and 1. Okay, so if we start with this prior, play the arm NIT times and observe SIT successes, then what's the posterior distribution for this parameter at the end of T rounds? We worked that out earlier. We saw that a beta prior is conjugate for Bernoulli observations and that the posterior distribution is obtained in this way. So you add the number of successes to the first parameter, the number of failures to the second parameter. So this is the posterior at the end of the Tth round. Okay, so yeah, we assumed that the first term was better and denoted the gap in the expected rewards of the two arms, the gap between them by delta. If we can bound the number of times that the suboptimal arm 2 is played up to time t, we can also bound the regret. Indeed, every time that arm 2 is played, a regret of delta is incurred because we get an expected reward mu2 rather than mu1, which we could have got by playing the best arm. And so the regret is the difference, delta. And hence the regret up to any time t is delta times the expected number of times the second arm is played up to this time. Okay. And here there are two sources of randomness in the algorithm. There's the randomness in the rewards every time an arm is played. That's always there. But because we are taking a Bayesian approach here, there's an extra randomness coming from how we sample from the arm distributions. So every time we want to decide which arm to play, we draw a sample from each of the posterior distributions, compare them, and play the arm which gave us the bigger sample. So that sampling also introduces randomness. And so this expectation should take account of that randomness as well as the randomness from the rewards on the place of the arms. Okay, so that's an expression for the regret. Okay, and how do we bound this? So let's denote by theta sub I of t, the random sample, we get a time step t for the parameter of arm I. And the suboptimal arm is played only if theta2 was at least as big as theta1. If it's bigger, the arm is played. If it's equal, then you have to decide how these ties are broken. Okay, so for any capital T, we can upper bound the regret up to time capital T as follows. So it's delta times the expected number of times that arm 2 is played up to this time. So we want to add up for little t equals 1 to t, the expectation that arm 2 is played at time little t. That's an indicator random variable. It's either played or not played. So the expectation is exactly the probability that arm 2 is played, which is at most the probability that theta2 is at least as big as theta1. And it's exactly equal if ties are always broken in favor of arm 2. In fact, it's exactly equal anyway because the probability of a tie is 0. These are continuous random variables, beta random variables. Okay, so we have an expression for the regret. So we are done, right? Not exactly, because this probability is not easy to calculate or even to bound, because these distributions are not given to us. They depend on the history up to time t. So theta2 and theta1 are beta random variables, but if we were given the parameters of the beta random variables, this would just be a calculation, this probability. But we are not given the parameters. The parameters are determined by the history up to this time. They are determined by how many times each arm was played and what the number of successes were. But the number of times each arm was played is in turn determined by these parameters in the past. So there are complicated dependencies here, and it's not easy to work out a bound on these probabilities. Okay, so in fact, we are not going to do this. We are not going to analyze the Thompson sampling algorithm because it's too hard. Instead, we are going to analyze a simplified version of the algorithm, which uses a genie. We are going to assume that we have a friendly genie who will tell us the value of mu1, the reward probability on the first arm. Okay. The genie knows which is the better arm and gives us the parameter for that arm. We don't know which is the better arm. So we only know that the genie has given us the parameter for one of the arms, and we have to decide how often to play the other arm, under what circumstances to play the other arm. Okay, is the setting clear? Take a moment to think about it. The genie gives us the value of mu1, and we have to decide when to play arm 1 and when to play arm 2. And a priori, we know nothing about arm 2, so we start with a beta 1,1 distribution for the parameter mu2. Okay, so the natural modification of Thompson sampling to this setting is as follows. So the genie has already told us the parameter of arm 1, so we will not have to sample for this parameter. So we have no uncertainty whatsoever about mu1. There's no prior, we always know mu1. So it's only mu2 about which we have uncertainty. So at the start of round t plus 1, we sample this parameter. We guess theta2 t plus 1 is our guess of mu2 in round t plus 1. And we guess this from the posterior distribution for mu2 at the end of round t. And as we already saw, that's a beta distribution with these parameters. So we add the number of successes up to that round to 1 for the first parameter, and we add the number of failures to 1 for the second parameter. Okay, and then if the sample turns out to be at least as big as mu1, which we know, then we play arm 2. And if it's smaller, we play arm 1. Okay, so it's exactly the same as Thompson sampling, except that for arm 1, there's no uncertainty. So we are, if you like, the prior distribution was always concentrated at mu1 from the start. So the posterior distribution is always concentrated at mu1. Okay, so if we end up playing arm 2, then we update the number of times this arm has been played and the number of successes we observed. And based on that, we also update the posterior distribution. So this is the algorithm we are going to study now, and this is easy enough to analyze exactly. So let me remind you again of what we are trying to do. We are trying to analyze the Thompson sampling algorithm. We decided that's too hard, so we invoked a genie and obtained a modified Thompson sampling algorithm where we have the help of this genie, and we are going to bound the regret of this modified Thompson sampling algorithm. Okay, so this will only tell us a limited amount about the algorithm we are actually interested in. It'll only give us, it'll give us an upper bound on a lower bound on the regret. It doesn't seem that helpful, maybe. But to the extent that the analysis will be pretty tight, we do in fact get a lower bound on the regret of Thompson sampling. Because so do we do worse with the help of the genie than without it? No, because we could always ignore whatever the genie told us and use Thompson sampling instead. Well, that's not entirely true. I haven't proved that this modified algorithm does better than Thompson sampling. I've just presented it as something that we intuitively believe does better. Okay, so we can't even claim that what we get is a lower bound on the regret. Nevertheless, intuitively, it seems like it should be a lower bound on the regret of Thompson sampling, and that we should do at least as well with the help of a genie. So that's the setting we are going to analyze. We won't analyze the Thompson sampling algorithm, but we stated a theorem proved elsewhere earlier. And when you see the analysis of the algorithm, you'll see that of the genie-assisted algorithm, you'll see that we get all the scaling parameters, right? We get the correct scaling of logarithmic in time and 1 over delta, where delta is the gap between the arms. We get different constants for the genie-assisted algorithm than what was stated in the theorem, but we get the same form of the scaling relationship. Okay, so let's start with the analysis of the genie-assisted algorithm. So let's fix time horizon t in the natural numbers. We are going to calculate the regret up to this time. And we'll define L as this quantity. So it's essentially 2 log t over delta squared, but we round it up to the nearest integer. And then tau is going to be defined as the smallest time little t by which arm 2 has been played at least L times. Okay? So tau is the smallest such time. Of course, it could happen that there's no such little t, that by time capital T, the arm has still been played, arm 2 has still been played fewer than L times. And by convention, the infimum of an empty set is taken to be plus infinity. That won't matter to our analysis. So you can just think of tau as the first time that arm 2 has been played at least L times, which may happen after capital T and which may even never happen. Okay, and as we saw earlier, the regret is related to the number of times that the suboptimal arm 2 is played, the expected number of times. And we are going to bound this as follows. So we show that after time tau, for any time little t after this, the probability of playing this arm and the event of playing this arm is that the posterior sample from the distribution for mu2 exceeds the known value of mu1, right? So that's the only circumstance under which this arm is played, and we show that the probability of this event is bounded by 2 over t. Hence, the probability of playing arm 2 in any such time step after tau is at most 2 over t. And we use this lemma to bound the regret. Recall that every time arm 2 is played, a regret of delta is incurred. Now, by definition of tau, the number of times that arm 2 is played up to time tau is exactly L, if tau is smaller or equal to T, capital T. If this arm was not played L times up to time T, then it's strictly smaller than L and the regret is even smaller. So up to time tau, the maximum regret we can incur is delta times L. Okay. And what happens after time tau? In each time step, there's at most a probability 2 over t of playing it. There are at most t time steps, in fact, t minus tau time steps. So the number of times, the expected number of times arm 2 is played after this time is just 2. After time tau is just 2. And the regret delta is incurred each time, so that gives us an extra factor of 2 delta. And so the total regret up to time t is at most delta times L plus 2. Okay. So assuming the lemma, we've proved the corollary. And what remains is to prove this lemma. We'll do that in the next lecture, and that will complete the analysis of this modified Thompson sampling algorithm. Okay, so take a moment to make sure you understand the statement of the lemma and all the terms that went into defining it. And make sure you understand why this corollary follows from the lemma. Okay, and one small remark, the parameter capital L here depends on t and on delta, and we have not made it explicit in the notations. Okay, delta is fixed, but for each time horizon t, there will be a different value of L. This is just for the analysis. The algorithm itself doesn't care about the time horizon. Okay, we are not optimizing things for a specific time horizon. We have an algorithm that keeps running indefinitely, but we analyze it for a particular time horizon and say for this choice of time horizon, this is the regret we incur. But the algorithm is not optimizing for any particular value of capital T. It's, if you like, simultaneously trying to optimize for all possible capital T. Okay, so I'll stop this lecture here, and we'll deal with the proof of this lemma next time, and that's the last step in the analysis of Thompson sampling.